Okay, I've said a little bit about this already, but I want to talk about what happens when you have a complex eigenvalue. Because it's not so easy to see the complex eigenvector in the vector field in the same way that we were able to in the real eigenvalue case. But it still has a big impact on the qualitative behavior of our solutions. Okay, so let's talk about that. So let's say that we have a complex eigenvalue. Let's say we have a complex eigenvalue. And remember, they come in complex conjugate pairs. So let's say we have something like lambda equals a plus bi. Well, sorry, a plus or minus bi. Because again, they come in complex conjugate pairs. And remember, I keep telling you, it doesn't matter which of the complex conjugate pair you use. Remember the idea. Once you have that complex eigenvalue, you use you find the complex eigenvector, and then you use the ansatz, and then use Euler's formula to find the real part and the imaginary part. And those are real valued solutions, linearly independent. That's just a quick review in a nutshell. Let's talk about what happens in various cases for A, because evidently the sign of B doesn't matter. So let's say A is, let's start with A equal to 0. If A is equal to 0, then we get what are called elliptical solutions. And the vector field itself is called a center vector field. Okay, these are just pieces of terminology. All right, let me show you a picture. So the picture that I want to show you is this one. Here is an example. There you go. This is a picture, obviously, of something elliptical. It's centered at the origin. What we see is that the solutions orbit around 0. Solutions orbit around 0. Okay? Great. That's what happens when A is 0. We get these nice periodic solutions. Okay, the feeling that you can feel maybe is that this has something to do with this unrealistic damping free case where there's no damping. Maybe this is sort of related to that. Anyway, that's a sort of a more qualitative statement. How about if A is greater than 0? Then in this case, we get what are called spiral sources. This is where we're spiraling away from the equilibrium solution, 0. Yeah, spiraling away. That's a spiral source, okay? So let me show you an example of that. Here. Copy, paste. Here we go. That's a spiral source. We are spiraling away from 0. Now, to tell that we're spiraling away from 0, you need to look carefully at the vector field. And you can see that the arrows of the vector field are pointing away, are having a spiral away from the origin. Okay? So if we're a tiny particle following this puppeted by this differential equation or system of differential equations, then if we are a little bit off of 0, even if we're very, very, very close, eventually we're going to recede away from it quite dramatically. Okay, that's a spiral source. And finally, one last case, if A, of course, is less than 0. Then what we get is a spiral sink. Picture this picture. Relax, buddy. Can I? Yeah, there we go. Copy. And then paste. Allow paste. I have no idea why it keeps asking me that. Seems like if I give, maybe I'll just. Is this okay to do? Oh, it cuts it off. Okay, that's not okay then. Let's do it like this. Just a little bit smaller. Okay. Again, to tell that this is a sink, you need to look at the details of the vector field. And you can see that the arrows point in the direction of sinking toward the origin. hope you have that feeling. Okay? So that's it. That's all I want to say about this case. In the next, or in the complex eigenvalue case, in the next one, what I want to do is go through the gory details of calculating from scratch the complex eigenvalue, the complex eigenvector, write down the general solution, and then use that to use all that information to give us a qualitative picture of solutions to the differential equation. I'm doing this in part because I think it's important for you to see more calculations involving complex eigenvalues. Okay? See you in the next one.